knows a lot about the science stuff. Professor Dave explains.
Quantum electrodynamics, or QED, is the quantum field theory that describes how particles interact with the electromagnetic force, and how electromagnetic fields influence the behavior of particles. It is widely considered to be the first successful quantum field theory combining quantum mechanics and special relativity. Additionally, it provides one of the most accurate predictions in all of science. For these reasons, studying QED can be an insightful entry point into the world of modern physics and the theory behind the standard model. The history of QED dates back to the early 20th century when classical electrodynamics, also known as Maxwell's equations, could no longer explain phenomena like black body radiation and the photoelectric effect. Quantum mechanics emerged to explain atomic-level phenomena, but it wasn't until the 1920s and 30s that scientists attempted to apply quantum ideas to the electromagnetic field itself. The Dirac equation, which we discussed earlier, laid the groundwork for QED to be developed by pioneering the first wave equation that was compatible with both quantum mechanics and special relativity. Throughout the 1940s, the theory of QED was developed separately by Feynman, Schwinger, and Tomonaga. Additionally, Feynman's diagram method made it easier to calculate the probabilities of particle interactions, which was a valuable contribution to the utility of the theory. In 1965, Feynman, Schwinger, and Tomonaga shared the Nobel Prize in Physics for their work on QED. Today, QED is considered the most precisely tested theory in physics. For instance, it correctly predicts the anomalous magnetic moment of the electron to a precision of 9 significant figures. This is considered to be one of the greatest triumphs of the Standard Model. At the heart of QED is a simple idea. Charged particles interact by exchanging photons. Since these photons are the force carriers of electromagnetism, exchanging these photons is how the electromagnetic force is mediated, and how the fields are able to interact with matter. But here's the interesting part. Photons involved in these interactions aren't all ordinary light particles. They are called virtual photons, and they can't be detected because the detection of these photons would violate conservation of energy and/or momentum. These virtual photons pop into existence only during interactions and then disappear. They don't exist long enough to be detected or observed, thus preserving the essential symmetries of a process, but they mediate the force and change the momentum of the particles involved. For QED, the relevant gauge is called U1, which corresponds to a symmetry of rotation around a circle in the complex plane, or multiplication by e to the I times theta. This comes from the fact that absolute phase is impossible to measure in electromagnetism. The arbitrary phase and U1 transformation within QED is one of the simplest examples of how gauge theories are present in the Standard Model. However, photons can also be emitted or absorbed in a way that makes them real. When a charged particle emits a photon that doesn't get absorbed immediately, like in the case of visible light or X-rays, it becomes a real detectable particle of electromagnetic radiation. At this point, their behavior is governed by a version of Maxwell's equations that is compatible with quantum mechanics and special relativity. These equations can actually be derived from within the U1 gauge theory. This dual nature of photons in QED, as both virtual mediators of force and real carriers of radiation, is part of what makes the theory so powerful and comprehensive. Additionally, like any good theory, it isn't just conceptually elegant and good at explaining what we already know. It has predictive power, and can be used as a tool for doing calculations to determine the probability of different interactions occurring. As we briefly discussed before, Feynman diagrams are a mathematical shorthand for calculating interaction probabilities. We talked about how each element in a Feynman diagram corresponds to a specific mathematical expression. In the context of QED, Feynman developed a set of rules that explicitly detail how to turn the diagrams into mathematical expressions. To introduce Feynman's rules, we'll work through a sample QED calculation. In this example, we will calculate the matrix element, also known as amplitude M, for a simple QED process, electron-electron scattering, also called Mahler scattering. We find m because m squared appears in the formula for the cross-section of the interaction, and we've previously discussed the importance of cross-section for describing particle scattering. This image represents the lowest order diagrams corresponding to this QED process. In the figure on the left is a direct diagram where one electron comes in with momentum p2 and leaves with p4, and the other electron comes in with p1 and leaves with p3. On the right is a twisted diagram where the incoming p2 electron leaves with p3 and the incoming p1 electron leaves with p4. Both of these diagrams are needed due to the fact that the electrons are identical particles, so we cannot say for certain whether the electron with momentum p1 leaves as p3 or p4. The same applies for the electron with momentum p2. To perform this calculation, we'll need to use a few of Feynman's rules for QED. For simplicity, we will use natural units. This is a convention used often by theoretical physicists in which h bar equals c equals 1. First, we will assign each external line with a momentum, p1, p2, etc. External electron lines are u of p and s, and external positron lines are u bar of p and s, where p is the momentum and s is the spin state. Note that these are spinors, as we've previously discussed. Each vertex in the diagrams will pick up a vertex factor, which Feynman's rules tell us will be I times GE times gamma mu, where we defined the dimensionless coupling as GE. For QED, GE is just E, the electron charge. Momenta are conserved at vertices because of conservation of momentum, so we can construct a vertex momentum Q that is the sum or difference of the proper incoming momenta P1, P2, etc. Remember, these propagators can be virtual, so the relationship momentum squared equals mass squared is not necessarily enforced, even though the Feynman diagram conserves momentum at the vertex. The final element that appears in these diagrams is the propagators, which are photons in this case, since we are dealing with QED interactions. The Feynman rules tell us that the photon propagator will be negative I times g mu nu divided by q squared. In the direct diagram, the electron with momentum p1 scatters into p3, and the electron with momentum p2 scatters into p4. The internal momentum carried by the virtual photon, q, is therefore q equals p1 minus p3, and q is also equal to p4 minus p2. This must be true because of conservation of momentum. Also, by setting q equal to the proper sum or difference of momenta here, we have avoided the need to deal with any delta functions or integrals explicitly. This cannot always be done. Applying the Feynman rules in the opposite direction of the arrows for each fermion line and writing down the terms from left to right, we find that I times m direct equals the photon propagator, negative I times g mu nu divided by q squared, times the outgoing electron term, u bar of p3 and s3, times the vertex term, I times GE times gamma mu, times the incoming electron term, u of p1 and s1. This is all multiplied by the same three terms for the other electron, the outgoing term, u bar of p4 and s4, the vertex term, I times GE times gamma nu, and the incoming term, u of p2 and s2. Collecting the factors of I, we see that I times GE all squared times negative I equals I times GE squared. After dividing both sides by I, plugging in q, and multiplying g mu nu by gamma nu to turn it into gamma mu lower index, which is called contracting indices, we can find that m direct equals ge squared divided by p1 minus p3 squared times u bar of 3, gamma upper mu u of 1, times u bar of 4, gamma lower mu u of 2. Note that m direct is a scalar because we have contracted the indices. We have borrowed a shorthand from the Griffiths text where u of some number I is defined as u of pi and si, and same for u bar. For the twisted diagram, the electron with momentum p1 scatters into p4, while the electron with momentum p2 scatters into p3. The momentum carried by the photon is now q prime equals p1 minus p4, or p3 minus p2. Repeating the same steps as before, with the exchanged final electron momenta, gives us m twisted equals ge squared divided by p1 minus p4 squared, times u bar of 4 gamma upper mu u of 1 times u bar of 3 gamma lower mu u of 2. You may have noticed that m twisted is just m direct, but has 3 swapped with 4 everywhere. If you think about the difference between the direct and twisted diagrams, this makes a lot of sense. The amplitude m twisted is truly just swapping p3 and s3 with p4 and s4 from m direct, since the electrons are identical. Now to combine the diagrams and amplitudes. The last QED Feynman rule tells us that since the twisted and direct diagrams differ only by swapping two outgoing electrons, we add a minus sign between the amplitudes. This is because electrons are fermions, and swapping identical fermions always adds a minus sign. Thus, the total matrix element, or amplitude m, for the QED process of electron-electron scattering is the following equation. Using these techniques, QED can be used to describe interactions between photons, electrons, positrons, and heavier fermions like muons. Each process within QED has an order, which describes the power of the fine structure constant alpha involved in the process. The higher the order of the process, the less likely it is to occur. This is because the value of alpha is approximately 1 over 137, so higher powers of this small number suppress the probability of each higher order. Additionally, while QED was originally developed to describe the interactions of electrons and photons, it also plays an important role in understanding the behavior of quarks. Since they are electrically charged and interact with photons, QED provides the framework with which to calculate the electromagnetic contributions to their interactions. Quarks will be discussed in more detail in the next tutorial, where we'll talk about quantum chromodynamics. In summary, quantum electrodynamics is one of the most successful theories in all of physics. It provides a framework for understanding and calculating how charged particles interact via the exchange of photons, and can be leveraged for all types of processes, from basic scattering to intricate higher-order corrections, by using Feynman's diagrams and rules. Now on to QCD.
Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.